Just as we calculate the enthalpy change for any chemical reaction from tabulated values for each product and reactant, we can do the same for the entropy change. However, rather than measuring entropies relative to an arbitrary zero, we can tabulate an absolute entropy for each chemical species. The third law of thermodynamics states that a perfect crystal at absolute zero has an entropy of zero. This allows us to have a well-defined zero for everything. We can therefore calculate the entropy change for any chemical reaction. But how do we calculate the entropy change for the remaining universe surrounding it? The only way we can calculate its entropy, or disorder, is through the transfer of energy in the form of heat. Transferring energy in the form of work really has no effect. Does a block of metal have any more disorder 10 feet off the ground than 5 feet off the ground? No. But the transfer of heat does speed up the molecules in the remaining universe if the reaction is exothermic. If the reaction is endothermic, the loss of heat from the environment will slow down its molecules. We can calculate this effect, but is there an easier way to determine if the overall entropy change of the universe is positive or negative, or in other words, determine if the reaction will occur or not? The answer is yes. Gibbs studied reactions occurring under a constant pressure. In this regime, the value of the heat transfer is equal to the enthalpy change. Substituting this within the expression for the entropy change of the surroundings, Gibbs finished with an expression that includes only the enthalpy and entropy changes within the chemical reaction itself. Everything is now focused within the system. In doing so, Gibbs defined the Gibbs free enthalpy change, or delta G, that simplifies the question of spontaneity for chemical reactions under constant pressure. If the change is negative, the reaction occurs. If it is positive, the reaction does not occur. And finally, for a system at equilibrium, the value of delta G is 0. And just as we did for enthalpies, we can tabulate Gibbs free enthalpies of formation for every possible compound, again relative to their elements in their most stable forms. Beyond telling us if a reaction occurs or not, the Gibbs free enthalpy change tells us the amount of useful work that can be done by a reaction. Though heat and work are two forms of energy and can be seamlessly converted one into another, not all the heat of a chemical reaction can necessarily be used to do useful work. Imagine the combustion of hydrogen gas with oxygen gas. The result is an incredibly exothermic reaction, with water as the final product. However, not all of the heat can be converted into useful work. The reaction has a considerable drop in entropy as we go from gaseous reactants to pure water. If all the heat were converted into work, the entropy change in the system would be negative, and the remaining universe would be 0. The entropy of the universe would thus decrease. The universe will not permit this. Some heat must absolutely be lost to the surrounding environment, at least enough to ensure that the entropy of the universe increases by some small value, if not more. What remains is the heat, or enthalpy, free to do useful work. This is why we call it Gibbs free enthalpy change.